Okay, this is a video about tolerance. So in engineering, we have dimensions on everything, right? Like, for example, this little Post-it pad is 3 inches. So let's call that nominal dimension. So the nominal dimension of this is 3 inches. But let's say you were going to draw this in the CAD system. You would make it exactly 3 inches, 3.000, exactly 3 inches. But if you were manufacturing it, there's no way to make it exactly 3 inches. You just can't do it. So what you do is you specify a tolerance. Like, for example, you could say, make this thing 3 inches plus a certain amount is okay, and then minus a certain amount is okay. Like say plus a millimeter and minus a millimeter. So then if it was plus a millimeter and minus a millimeter, the range on that, the 1 millimeter over and 1 millimeter under, would be 2 millimeters. So we would say the tolerance is 2 millimeters. So that's the basic idea with tolerance. We can't make something exactly, so we have to specify a range of dimensions that are acceptable. So here's a drawing that has a bunch of tolerances on it. So see, it's a 2-view orthographic drawing, right? This is call this the side view and the front view. And this happens to be a sectional. They've cut this thing in half and shaded the part where the material has been cut. And let's just look at some of these numbers. So like this outside dimension here is the how tall this thing is, or it's actually the diameter. So this symbol here means diameter, and these two numbers are specifying the minimum and maximum values that this thing can be. So they're saying that this thing can be no more than 5.00 inches and no less than 4.92 inches. So they're calling it out to 2 decimal places, right? So they're assuming that the person that's manufacturing this, or the machine that's manufacturing this, can hold a accuracy of at least 2 decimals. Like this little ruler right here, it's accurate on the top to an 1/8 inch. It's accurate on the bottom to a 1/16 of an inch. So this thing here, they're saying this thing is accurate to 0.00 x. It's to at least 2 decimal points. Okay, so you can specify this. It looks like a fraction, but it's not. It's a range, right? So the biggest value is 5 and the smallest value is 4.92. And then the tolerance is the difference between these. It's just 5.00 minus 4.92, or 0.08, right? So the tolerance on this would be 0.08. Okay, here is another way to specify a tolerance, and it looks like subtraction, but it's really just the biggest allowable value and the smallest allowable value. And once again, this symbol here means diameter. So they're saying that this distance, actually this distance here, which is this circle, right, has a diameter of at least 0.783, or rather, the other way around, at least 0.781 and no bigger than 0.783. So you can make this hole any size between these two, and that's okay, right? So the tolerance is the difference between these two. It would be 0.002, right? Because this number here minus this number, the difference is 0.002. So those are 2 of the ways that you represent tolerances, either as numbers on top of each other, or this thing. The other way you might see this is you might, like this dimension could be specified as 5.00 plus 0.000, minus 0.008, something like that. Or, it could also be specified as somewhere in between there, like 4.9, since the range is 0.8, you could go 4 over on either side. So in between, the middle value between these would be 0.496 plus or minus 0.004. So then if you added 0.004 to this, you'd get 5 exactly. And if you subtracted 0.004 from this, you'd get 4.92. So those are three ways to specify a tolerance, either min and max over each other, put the dash in between, or you can do this base dimension, you could call it, and then a plus value and a minus value, or you could make the plus and minus values the same. Here they're not the same, but here they are the same. Different ways to specify the same thing. All right. So let's work some increasingly difficult problems. So here's just a simple tolerance on the length of something. So we're saying this thing is 4 inches plus or minus 0.005. Okay, 0.005, sometimes we say 5 thousandths because the decimal points, the digits after the decimal point are tenths, hundredths, thousandths. So this is 4 inches plus or minus 5 thousandths, we sometimes say. So you could specify it this way, or you could specify it this way as a fraction. You could say the biggest it could be is 4.005, right? Or the smallest it could be is subtract this 4.005, and it would be 3.995. Okay, then the tolerance, okay, we sometimes say is the difference between these two numbers. So this number minus this number is 10 thousandths. Okay, so that's just a simple length tolerance calculation here. Sometimes we have several tolerances together that add up. We call that tolerance stacking. And here I have a little part with a fat part right here and then a skinny part right here. And this thing is approximately 2 inches long. And this guy over here, the part that sticks out, is 1 inch long. And both of these lengths have a tolerance on them. So this guy is 2.005 over 2.000, so it has a tolerance of 5 thousandths. And this guy here has a tolerance of 10 thousandths. Biggest value is 1.010, smallest value is 1.000. And so what's the tolerance on X, right? So the range or the tolerance of values, of acceptable values on X is, well, there's going to be a max value and a min value, right? And the max value on X happens when this value, this distance here is at its max, and this distance here is at its max. So X max is this biggest value over here, so 2.005, plus the biggest value over here, 1.010. So it's going to be 3.015. Okay, and then the minimum X value, the smallest that X could be, is this smallest value, or 2.000, and plus this smallest value, 1.000 or 3.000. So X is these two numbers here. So you can write it as a fraction if you want. So X is 3.015 over 3.000 with a tolerance of 15. The difference between these two values, the difference between the max value and the min value, is the tolerance, and that's 15. So this if you were specifying a part like this, it's hard to make this. It's hard to maintain all three of these tolerances. So try not to stack too many tolerances when you're designing things. All right, so that's just basic length and tolerance stacking. The next level of complexity is putting things inside of each other. So we have two kinds of fits that we're going to talk about. We have clearance fits, where there's some space between two things. You put something inside of something else, and there's a little gap in there. Okay, that's a clearance fit. And then there's an interference fit, where you're forcing something in, where the space between is actually smaller than the thing you're putting in, and you're forcing it in there. It's an interference fit. Okay, there are other fits in between here that are in the book, but I mean, you don't need to look at those. clearance and interference is enough to understand the concept. And if you find yourself working in an industrial environment where these other kinds of fits matter, it would be an easy thing for you to research that and look it up. But for now, let's just do clearance fits and interference fits. So the first thing here is a clearance fit. So let's say we have a shaft. Okay, now let's say this is a 1-inch shaft, which we sometimes use the term nominal because nobody wants to go around saying these numbers all the time. So we just call it a 1-inch shaft. So that would be the nominal size. Okay, 1 inch. So given a 1-inch standard shaft, now these are tolerances on a certain kind of shaft used in industry. These are shafts that poke out of motors and connect pieces of rotating machinery and stuff. So let's say it has these dimensions. So it's maximum of 1.000, minimum of 0.998. So a tolerance of 0.002, right? The difference between these two. Now, let's say we want to slide this shaft into a hole like this. Right? You want to take this shaft and put it in this hole. This hole could be a bearing or a coupling or some other piece of machinery. So there's going to be a tolerance on this hole, okay? And there's going to be a tolerance on this gap. Right? There's 3 tolerances involved here. There's the tolerance on the shaft, which is given. There's the tolerance on the hole, which we need to determine. And then there's the tolerance on this gap. So let's assume that tolerance on the gap, this gap here between the shaft and the hole, is 0.15 to 0.20. So you want this gap to be somewhere between 0.15 and 0.20. We call that the clearance, by the way. So the tolerance on a gap between two things is called the clearance. So where did this 0.15 to 0.20 come from? It's just made up. Now, there's lots of reasons for different tolerances. It depends on what you're trying to do. Like, you're trying to squeeze oil in there? Are you, do you want it to just barely fit? What are the rates of expansion of these materials? What's the lifespan? All kinds of factors, but that's beyond the scope of this course. So let's say you're given this shaft and you're given this clearance. Okay? How big is the hole? So there's going to be 2 dimensions on the hole, max and min. And I've given you these little formulas here. So hole max is smallest shaft plus biggest clearance. Okay, so you may have to rearrange this algebraically for the harder problems we're going to do, but for the easy ones, just find the right formula here. So keep in mind, this is the maximum allowable hole. It's not the maximum possible hole, but what we want is the maximum allowable hole. That is, how big can we make the hole such that when we put in a part of a different size, the clearance is still acceptable. It's a little bit confusing, and it's actually possible for me to talk about this too much. So just follow these examples. So the biggest this hole can be, okay, will happen when you happen to, okay, so think about it this way. You've got a bin full of these shafts, and you just pick one, and it's going to be somewhere in this range, but you don't know where in this range. So let's say you pick the smallest shaft, okay? And then you pick the biggest clearance. Okay, that's the condition for the largest hole. Okay, so the smallest shaft is 998 and the biggest clearance is 0.20, right? So add those together, you get 1.18. That's the biggest the hole can be allowed to be, right? And so that's the formula, and just use the formula. Now, if you want to think about this a little bit more and try and understand why this formula is the case, you can. It can be a little confusing, but let's see if I can say this without being too confusing. So let's say you made the shaft bigger than this 998, then the clearance would become smaller, and that should be okay. And if you went all the way down to 1, then the clearance would be 18, which is still in this range, so it's okay. What about if you made the clearance smaller? Then it would still be okay, right? Because you'd be dropping down to 15. This would become, if you dropped 5, it'd be 01. 012. Well, we need to keep working to see if 012 is okay, right? So let's keep going. So I'm fighting my own confusion, to be totally honest with you. And I've worked with these for years, and these can be confusing. So I have these formulas and use those. But keep in mind, we're interested in the allowable sizes, not the maximum possible sizes. Okay, and I'll show you another way to double check this in a minute. But anyway, use this formula to get the max. Use this formula to get the min on the hole. It's biggest shaft plus smallest clearance. So biggest shaft is going to be 1.000. Smallest clearance is going to be 0.015. So you get, you add these up, you get 1.015. And this is what that looks like if you draw it out. So thus, you specify the hole to be between 1.018 and 1.015. Okay, this is the practicality of how to do these things. Now, if you are interested in understanding this a little bit more, where did these formulas come from? There's, you can think of it like this. So this is a slip fit. And what I've done is I've drawn all 4 combinations of biggest and smallest, right? So we have a shaft that's 1.00 to 0.998, okay? And we have a hole that's 15 to 10 thousandths over 1, and then we have a clearance of this 1017 thing. And do this first. So this is the situation of biggest shaft, smallest hole, right? So biggest shaft is 1, smallest hole is 10. The minimum clearance would be 10 thousandths. Okay, then do this one next. So this is smallest shaft, biggest hole. There's smallest shaft, 998. Biggest hole is 015. Just using these numbers down here of smallest and biggest, I end up with a maximum clearance of 17. So you solve these first, and you end up with a minimum clearance, this gap here of 10, and max of 17, this gap here. Then the other 2 cases, the clearance will fall between 10 and 17. You see, the clearance is 12 here, and the clearance is 15 here, which is between 10 and 17. And that's the other 2 cases where you have smallest shaft and smallest hole, 998 and 1010 for smallest hole and shaft, and that it works out to 12 thousandths, which is in the range here. And biggest shaft, biggest hole is 15, biggest shaft is 1, you end up with a 15 clearance. So you see, you can get any combination of these, and they'll fall within the acceptable range here. And that's kind of where the formulas that I'm talking about come from. So think about this, okay? Spend some time just kind of staring at it and scratching your head and thinking about it. Let's look at the, so one more problem is interference. So this is the other extreme of putting things into holes we call interference. Remember, there's clearance and interference, and then a bunch of other kinds of fits in between, like a sliding fit and other things that are in the book. But interference means that the thing you're putting in the hole is bigger than the hole, and you're just going to force it in there. And that's what makes it stay, is that you just crammed it in there. A really simple example is a nail, where you just pound it into the wood. But we do this with metal and parts all the time, where to assemble them, we just specify these tolerances and we just press them together and they stay together. So let's use our same shaft, 1.000 and 0.998. And so somebody somewhere comes up with this interference, right? Like 5 to 10 thousandths interference. So somebody decided that this amount of interference will serve our purposes. It'll make the parts stay together. Now, it could be lots of factors. It could be material. It could be what the machine or device is being used for, like how much stress is on it. What are the thermal expansion rates? Lots of factors go into determining what this interference is. But let's just say you're given this shaft and you're given this interference. You want to figure out how big to make the hole. So use this formula, right? Hole max is smallest shaft minus smallest interference. And just plug in these numbers and you get the smallest hole. And then that looks like this. Okay, and then I've got a formula here for the, I'm sorry, so I mixed up max. So this is the formula for max, hole max. This is the formula for hole min. And just plug in the values and you get this. And you can draw it out and kind of show, here's our interference of 10, and here's our interference of 5. And so once again, use these formulas, and you might have to solve them. Like if you were asked for biggest interval, you'd move this to the other side, right? So biggest interval would be biggest shaft minus smallest hole, right? So you might have to do a little bit of algebra to find what you're using. But use these formulas because this material is kind of inherently confusing. You can get it a little bit clearer in your head if you think about this kind of thing here. Okay, but be careful. These are confusing. They still confuse me, and I've been doing this for years. All right. What's the homework? The homework, what would I like you guys to do? Well, do a hand sketching, because there's a certain amount of hand sketching we need to do in this class. So I want you to use pencils for this. So basically, take these two pieces of paper here and break each one of these little pictures out into one drawing, right? So take this little thing here and make it a big drawing that fills the whole page. So there'll be 12 pieces of paper. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 pieces of paper with these things sketched. Sketch these things out and then draw in the numbers here. Okay, I've done the first one for you, and perhaps I can make this zoom. Oh yeah, you can. Great. So I've done the answers on the first one. So we've got the basic size, or the nominal size. That's just when you're talking about this part, the number you'd use. Like you're saying, oh, it's 3.5 inches long. So 3.5 is the basic size, okay, for A here. For B, basic size is an inch, so write an inch. C, the basic size is 2.25. D, this is a hole. So they're giving you 0.24, but just round that to a 1/4 inch. So say 0.25 for the basic size, because in the inch unit system, we typically go by 1/4 inches, eighth inches, half inches, things like that. We don't really use 0.24 to talk about stuff. Like if it was a bolt, you would just say a 1/4 inch bolt, but it's not actually a 1/4 inch, right? So that's the basic size. All right. Then figure out these tolerances. So part A, see, it's +0 minus 0.02. So the difference between these is 0.02. So that's the answer here. Okay, then B, it's plus 0.01 minus 0.00. So the difference here is 0.01. The difference between these two numbers is 0.01. For C, it's plus or minus 0.01, right? So it could be over by 0.001 and under by 0.001, or the total of those is, or the difference between these, is 0.002 for C. And likewise for D, same thing. Okay, then what is the min and max value? So A, the max it'll be is 3.5 plus 0, so 3.5. The min that it could be is 3.5 minus 0.02, so 3.48. Okay, for B, the biggest it could be is 1 plus 0.01, so 1.01. And the smallest it'll be is 1 minus 0.00, so 1.00. This thing here, C, could be over and under by 0.001. So the base dimension is 2.25 or 2 1/4. So it's going to be 2.251 or 2 and 2.249, right? Over by 1 and under by 1. So like that. Then the harder one is tolerance stacking. So we want to know what dimension E is. Okay? So you're going to stack up A, B, and I called this one X. Okay, the other thing I changed is look at this here. The tolerance that they're giving you, or the over and under values they're giving you, is 0.3. That's so big compared to these others that it's just crazy, right? Like, you know, if you have to hold these to a high tolerance, but then you can all of a sudden be 0.3 plus and minus, it makes no sense. So it's got to be a typo. So I changed it to 0.03. So there's other typos in here. Change them if they don't make sense. But so E, what is E? So we need the biggest value that E can be and the smallest value that E can be. So think about it this way. If A gets bigger, right? If A was bigger, E would be bigger, right? And if B were bigger, E would be smaller, right? Because B would be taking up some of this A, right? And likewise, if X were bigger, then E would be smaller. So the formula is biggest A minus smallest B minus smallest X, right? Because X and B getting smaller make E smaller. Sorry, the other way around. X and B getting smaller make E bigger. And A getting bigger makes E bigger. So here's the formula. Biggest A minus smallest B minus smallest X. So the biggest A can be is 3.5. The smallest that B can be is 1.0. The smallest that X can be is 1.22. So that means the answer we're looking for is 1.28. And that's for max E, or biggest E. Likewise, the smallest E happens when A gets smaller, right? When A gets smaller, E gets smaller. And when B and X get bigger, E gets smaller. So here's the formula. So the smallest A is 3.48. The biggest B is 1.01. The biggest X is 1.28. So there's the answer. So do these. Redraw each one of these as a picture, as a hand sketch. Recreate the table, okay, as a hand sketch. Then do all these calculations and turn that in. So this is just some tolerance stacking for inches, some tolerance stacking for metric. Then here's a clearance fit for inches, an interference fit for inches, and then a problem that has both. And then the same thing for metric. So let me do some of this for you. So you've got this shaft with 9993 min and 9997 max, so it has a tolerance of 0.0004. This guy's got a tolerance of 0.0005. You take one of these out of a bin, stick it in, one of these. So grab one of these out of a bin, grab one of these out of a bin full of parts, put them together. What's the clearance? What's the gap between these two? is what we want to know. So first of all, they're asking what I already did, the 5 and the 4. And this is going to be 4 thousandths. This is going to be 5. That's these two numbers here. Then this one, okay, this box here, they're the same answer. So I just kind of highlighted the box because there's two columns, but really just one answer that in there because it's the clearance between A and B, which is the same for A as it is for B. Anyway, use the formula that I gave you on that other sheet. So the smallest clearance happens when you have the biggest, happens when you have the smallest hole minus the biggest shaft. So the smallest hole is 10000. The biggest shaft is 9997. So the minimum clearance is 0.003. Right? Then calculate the maximum clearance would be this box in here. These would have the same answer. And then the range between this and this 003 and which goes in here, and this one would give you the tolerance on the clearance. Okay? And then do that again for this other guy sticking in there. And this thing here, it's interference. They just haven't used shafts and holes. They've used sort of these little bumpy things stuck into this little groove thingy, but it's still an interference fit. Can you do those? Those are pretty straightforward. I don't think anybody will have too much trouble with these. Now this one's kind of hard because you're taking this guy and they're talking about clearance on J. So this shaft slides into this thing, and there's a clearance between these two parts. Okay, and then K, they're talking about interference. So this little donut thing presses into this hole over here. So there's an interference between these two parts. And they're giving you some knowns, mins and maxes on holes and things, and then they're giving you some pieces of the tolerance. So you're going to have to do some algebra, right? So this is a slip fit problem on this side, and then this is an interference fit problem on this side. You have formulas for clearance fit. You have formulas for interference fit. It's just the knowns and unknowns change. So you may have to go back to these formulas here and rearrange them algebraically to solve for the thing that you need. Okay? And work through that from knowns to unknowns, and it's a little bit of a challenge. I don't want to work it for you. I want you to work it. Okay, so draw these 12 drawings. 10 plus 2 is 12. Take pictures, or with your phone, stick the pictures in a Word document, save the Word document as a PDF and mail it to me, or however. That would be my preference, is one single PDF. All right. Hope everybody's doing okay out there, not going nuts. Bye-bye.